Hello, and welcome to the extra spooky October edition of the Dudley at Siena's Cosmic Adventures lecture series. My name is Mindy Townsend. I'm an astronomer with Dudley at Siena, and this month I want to talk about the dark side of astronomy. So, a huge part of the study of the universe is the study of light. That's really how it all started. The study of the sun and the moon and the stars. Cultures from all over the world looked at the night sky and created stories to entertain, but to also help them keep track of time and the seasons. For much of human history, astronomers were constrained by what we could see with our eyes. If we didn't see anything, there must be nothing there, right? But over time, we realized that there is still meaning in the nothingness, things it can teach us. And as we became more sophisticated observers, we realized that the nothingness was not so empty after all. When I ask people what they think of when someone says astronomy, often they will talk about the Hubble Space Telescope, which is on your screen right now. Hubble launched in 1990, and it was the first of NASA's great observatories, a suite of 4 space telescopes that could see the universe in different regions of the electromagnetic spectrum. While not the first space telescope, the images Hubble beamed back was really the first time that people everywhere could get a glimpse of deep space. Some of the most striking images are of nebulae, these gigantic clouds of gas and dust. These images would become iconic and forever associated with this telescope. These nebulae are emission nebulae. So emission nebulae are composed of vast amounts of ionized gas. So gas that has been heated up so much by the stars inside that the gas glows in optical wavelengths. When astronomers see this type of nebula, we know that the cloud is in the process of forming stars. We see the evidence of that through the glowing gas. But there's another type of nebula that is harder to observe, and that is an absorption or a dark nebula. Dark nebula are dust clouds like emission nebula, but the dust is so thick and dense that visible light is blocked. Teeny tiny particles of dust that are coated with frozen carbon monoxide and nitrogen don't let any light through. So to even know they're there, they need to be in front of a high contrast object like a dense star field or another emission nebula. So these nebula are primarily made of molecular hydrogen, which is important for star formation. In fact, we know that dark nebula are a locus of star formation because while the visible light is blocked, infrared light is not. When we look at these nebula in the infrared, we see gobs of stars. Dark nebulae are quite cold, between 5 and 10 Kelvin. So that's between negative 268 and negative 263 degrees Celsius, or negative 450 to negative 441 degrees Fahrenheit. So really, really cold. For star formation to occur, you actually want it to be really cold. When it's too hot, molecules will bounce around too fast and they will never kind of come together. But in a dark nebula, it's cold enough that gravity will be able to pull molecules together to form stars. There is a problem, though. So here we are, pulling hydrogen gas in and making it more dense. When a gas gets more dense, the temperature of that gas rises. So how do stars ever get made? The solution lies in the carbon monoxide-coated dust grains. Carbon monoxide is a very efficient cooler of molecular clouds, like a dark nebula. As the cloud starts to heat up, carbon monoxide and molecular hydrogen will collide more frequently. The hydrogen molecules will transfer some of its energy to the carbon monoxide, which will then radiate that energy out into space at a wavelength that can permeate the thick dust cloud. It's like a natural air conditioner for a gas cloud. So in this way, dense carbon monoxide-coated dust actually helps the star formation in these clouds. Dark nebulae can be divided further into two main types. So there's giant molecular clouds, and then there's Bok globules. Really, the difference between them is one of scale. Giant molecular clouds can have masses up to 100,000 times the mass of the sun and be hundreds of light years across. An example of a giant molecular cloud would be the Eagle Nebula, so a portion of which is seen at the top of your screen. The pillars of creation are part of the Eagle Nebula. The image on the left is actually the nebula in visible light. And you can see there's a lot of dense dust. We can't really see through it. But on the right is that same nebula in the infrared. And you can see just how many stars are being hidden within that nebula. Bok globules, on the other hand, are much smaller. An example of one is on the right of your screen, right here. It's located inside the larger nebula called NGC 281. And these Bok globules are named after the astronomer who first observed them in the 1940s, named Bart Bok. And they have masses of only around 50 times the mass of the sun and are only about a light year across. You may not realize it, but there are a number of famous and important dark nebulae. I'm going to start, though, with a less well-known dark nebulae because it's actually my favorite. It goes by the unassuming name of Barnard 68. It's about 400 light years away and contains about twice the mass of the sun with a diameter of only about half a light year. So what I like about this nebula is that it has very defined edges. You can see in this image. It really looks just kind of like a hole in the stars. This actually indicates that the cloud is in the process of condensing and will probably form stars in the next 200,000 years, which is a blink of an eye in astronomical terms. I like to bring up this nebula because it's the subject of some internet misinformation. A lot of people are claiming that it's actually a spot in space where there is absolutely nothing. No stars or gas or dust or dark matter or anything. And that isn't true. So check out these images of Barnard 68 from the European Space Agency. So going clockwise from the top left, these are images of this nebula in increasing wavelength. So the top row is the nebula in optical wavelengths, so visual wavelengths, and the bottom row is in the near infrared. So you can see for yourself, it's not empty space. In the bottom left image, especially shows there are many, many stars in this region of the sky. It's just that the light that those stars produce that are in the optical wavelengths are blocked by a thick cloud of dust. One of my other favorite nebula is one that most people probably wouldn't think of as a dark nebula, but it is. So it's the Horsehead Nebula. The Horsehead Nebula is in turn part of one of the most famous astronomical objects, the Orion Molecular Cloud Complex, and it's located in the scabbard of the constellation Orion. So kind of here's Orion's belt, if you can identify, oops, go back, identify Orion's belt. Underneath is the Orion Cloud Complex. It's about 1,375 light years away and 7 light years across. I love it because it really illustrates how these dark nebula are only discernible when viewed in front of something very bright. For Barnard 68, that bright thing was a really dense star field. For the Horsehead Nebula, that is this bright and beautiful emission nebula that surrounds it. You can see down here this wonderful, wonderful pink light really contrasts with the Horsehead. The nebula's distinctive jaw is thought to be caused by stellar wind coming off a giant star in the vicinity. The most famous image of the Horsehead Nebula probably comes from the Hubble Space Telescope, but it wasn't discovered by Hubble. It was actually first recorded in 1888 by Wilhelmina Fleming, who was one of the famous Harvard computers. Finally, and probably the most culturally significant dark nebula, is one that we in the Northern Hemisphere can't even see. It's the Coalsack Nebula. There are some astronomical objects that are visible in both the Northern and Southern Hemisphere, but really the Northern sky and the Southern sky are radically different. The Coalsack Nebula appears in the Southern Hemisphere only, and unlike other nebula I've mentioned, this is one that can really be viewed with the unaided eye. The Coalsack Nebula is about 600 light years away and embedded in the bright band of the Milky Way. Western explorers would often call it the Dark Magellanic Cloud to echo the Large and Small Magellanic Clouds, which are 2 satellite galaxies of the Milky Way that are also only visible from the Southern Hemisphere. You can kind of tell that the cloud isn't perfectly opaque. It's not like Barnard 68. Some light does get through, but that light is changed. So this is a process called interstellar reddening. Some starlight can peep through, but it will look redder to us than it actually is. This is caused by those dust grains in the nebula, which like to absorb and scatter blue light, leaving the red for us to see. In the Northern Hemisphere, we don't see a lot of these dark nebula that are embedded in the Milky Way. This is because the North Pole is pointed out towards the edge of the galaxy, while the South Pole is pointed towards the interior. This diagram on your screen illustrates this in a way, right? Draw your attention right here. The middle fuzzy line, so this is the Milky Way edge on, with the red dotted line indicating the orientation of Earth's axis of rotation, with the north pointing up. How the Earth is situated in the galaxy points the north out facing the edge of the galaxy and points the south towards the galactic center. This gives the Southern Hemisphere a better look at both brighter stars and more dark nebula. This might be the reason that dark nebula are more culturally relevant to people who have lived in the Southern Hemisphere for thousands of years. The Coalsack Nebula in particular is quite important. For example, in the Inca tradition, the creation god Ataguchu once became so enraged that he kicked the Milky Way, causing a portion of it to fly off and create the Small Magellanic Cloud. The hole that remained is the Coalsack Nebula. These are called dark constellations or dark cloud constellations, and they are fairly unfamiliar to us in the Northern Hemisphere. The constellations that we know and love are based on the ancient Greek, Roman, and Middle Eastern stories. The sky we in the Northern Hemisphere know really came kind of from this region here, the Mediterranean and the Middle East. It was a game of connect the dots, and the dots make shapes in the sky. We drew lines between the stars that represent important stories and cultural memory. The limitation, though, is that, Greece, the Mediterranean, it's in the Northern Hemisphere. Western astronomers didn't develop quote unquote official southern constellations until the 16th century. Because as we briefly discussed, the sky looks different in the southern hemisphere. So the Milky Way is brighter, and there is a great view of something called the Great Rift, which is a string of overlapping dark nebulae that contains over 1 million times the mass of the sun worth of plasma and dust running right along the spine of the Milky Way. First peoples who called the southern hemisphere home had a lot to work with when it came to studying and analyzing their night sky. The Inca, for example, had both luminous constellations, meaning constellations made of stars, and dark constellations. Luminous constellations tend to be inanimate objects, but dark constellations are alive. Dark constellations tend to represent living things that come to Earth or come to drink the celestial river, aka the Milky Way. These dark constellations usually reflect something that's happening on Earth. So this is a painting of the night sky as seen by the Inca by Cusco artist Miguel Aroz Cartagena that depicts some of these dark constellations. There are a number of these dark constellations spread throughout the Milky Way, and that appear at different times of the year. So first, let's talk about the Fox right here at kind of this edge of the Milky Way. The sun will pass through this constellation in December, which is significant because that is the time of year that baby foxes are born. So next is the Eye of the Llama and the Baby Llama, which rises in November. So this is arguably the most important constellation to the Inca because llamas were incredibly important to pre-Columbian life in this region. There is a little bit of an unusual dark constellation in that it incorporates a couple of stars, so Alpha and Beta Centauri, that serves as the llama's eyes. This constellation consists of a mother llama at the top and a suckling baby llama. I want to talk about the next constellations as a pair, the Tinamou, otherwise known as the South American ground partridge, and the frog. So this is the Tinamou right here where my mouse is, and this is the frog. The Tinamou seems to be chasing the toad, which is true to life because Tinamous tend to eat small frogs and lizards. Tinamous appear in the sky in October and stays until July, and its disappearance marks the end of the potato harvest. The toad also has meaning. It's not just food for the Tinamou. Toads are actually also very important to the Inca. It was thought that the more toads croaked, the more likely rain would come. So the appearance of the toad in the sky meant that it was time to start planting. The final dark constellation from the Inca tradition I want to talk about is the serpent, which is this large, winding dust cloud. The serpent is thought to oversee all snakes on Earth. The constellation will appear headfirst in August and begin to set in February, which matches the activity of real snakes in the Andes. The first peoples of Australia and the surrounding islands also developed dark constellations. The most famous is the emu in the sky, or the celestial emu. This is a fascinating one, I think, because the native people of Australia are not just one group. There are many language groups, and many of those groups have some iteration of the emu in the sky. This is one constellation, but depending on how it's oriented in the sky at different times of the years, it will tell you different things, as illustrated by these 4 images at the top. At different times of year, the emu will be oriented either so it appears to be running or sitting down. Depending on its position, observers knew if it was time to hunt emu or collect their eggs. I really love the emu in the sky. It really does look like an emu, right? This large, flightless bird that's native to Australia. I don't know about you, I can really see it in the dark nebula of the Milky Way. Maybe it shouldn't be surprising that it pops up across a bunch of language groups in Australia. The head of this very important constellation right here is actually the Coalsack Nebula, and the body is the Great Rift. Okay, so far I've talked about what we see when light from stars is obscured by dust. But there are things in the cosmos that we truly cannot see at any wavelength, and that we only know are there because of their effects on the surrounding universe. One of those things is a black hole. So black holes are a consequence of Einstein's theory of general relativity, which we will get to. But there was a kind of proto-black hole idea circulating in the early 1700s. This idea is credited to a natural philosopher and clergyman called John Michell, and he proposed that there could be a star massive and compact enough. You would need to go faster than the speed of light to escape it, meaning that the light the star emits would travel only a small distance before falling back onto the star itself. If a star like this existed, we would not be able to observe it directly because none of the light it emits could travel to our eyes, hence the name dark star. And what an idea this is, that there are stars in the universe that are literally too massive to see. Mitchell made one big assumption, though. He assumed that light was affected by Newtonian gravity, and at the time, it was not at all clear that that was true. At the time, physicists and astronomers thought that light was strictly a particle called a corpuscle. These things were like rigid balls of light bouncing around. However, in the late 1700s, it became clear that light is a wave. So this kind of spelled the end for John Mitchell's dark stars. It was thought that since waves are massless, that gravity could not affect them. If gravity could not affect them, then it's not possible for a star to get so massive and dense that it pulls its light back onto itself. Here's the thing, though. This is wrong. Gravity does affect light waves, but we're not really going to know that for a little while. So this idea of dark stars falls out of favor in the scientific community. We can fast forward a couple hundred years, and Albert Einstein publishes his general theory of relativity. General relativity is a theory of gravity as basically a manifestation of curved space-time and how gravity affects space-time. Physicists were working on finding solutions to Einstein's equations, and they were coming up with results that were unusual and difficult to interpret. What they found was that general relativity predicted the existence of regions of space with infinite density and zero volume. There were a lot of physicists who thought this was clearly impossible. Arthur Eddington was one of them. He was a very big deal in his day and did not believe such a thing was physical. To create this region of infinite density and zero volume, you need a lot of mass packed into a very small space. The only thing at the time that would have even come close is an extremely massive star, and which, while very massive, could not get dense enough to form a black hole. But in 1931, Subramanian Chandrasekhar proved that there are stars out there that are massive enough that when they run out of fuel, will collapse into something incredibly compact called a white dwarf, but that those objects would only form upon the death of less massive stars. More massive stars would collapse onto themselves even further and become even more compact and dense. I want to note that when Chandrasekhar did these calculations, he was literally on a boat to England from India on his way to start his graduate education in Cambridge. He was a kid when he figured this all out. And there was still a lot of resistance to this idea that stars could collapse on themselves like this. Physics heavyweights like Eddington argued vociferously and sometimes unkindly that Chandrasekhar's results were impossible. Einstein himself argued that black holes could not exist in nature, despite his theory predicting them. Despite this, the idea that compact objects like white dwarfs, neutron stars, and black holes exist in the universe did start to catch on. The math was there. While white dwarfs had been observed, other compact objects like neutron stars and black holes had not been observed. Until the 1960s, when Jocelyn Bell Burnell observed the first pulsar, which is a neutron star that seems to emit an energy pulse at regular intervals. After that discovery, black holes did not seem so improbable. Black holes are considered to be very exotic objects, and for good reason. They're weird, and it's really hard to wrap our minds around them, but they're also incredibly simple objects. Black holes are described by three observable properties: its mass, its angular momentum, so how it spins, and its electric charge. Because once something goes into a black hole, we can't get it out again. All the information about the stuff that went into a black hole is gone. The radius of a black hole, called the Schwarzschild radius, which is given by this equation here, is dependent totally on the mass of the black hole. It's described by this equation. G is a constant number. It's the gravitational constant. C is the speed of light, which is also a constant. So the only thing that changes is m, the mass. And the bigger the mass, the larger the radius. Even though black holes are very simple, that doesn't mean they don't have any structure. I think what we usually consider a black hole is actually the event horizon. And the radius is the same really as the Schwarzschild radius for simple black holes. This is the boundary of space-time through which matter and light can pass only inwards towards the black hole. This is the boundary where famously not even light can escape. Thank you. You can think about this in a couple of ways. So first, you can think of it as the boundary where the escape velocity, so the speed you need to move to escape a gravitational pull, is faster than the speed of light. Since nothing can move faster than light, nothing can escape. The second way you can think about this is a little weirder, and that is beyond the event horizon, the fabric of space-time is so twisted up that there is literally no path beyond the event horizon. There's no way you can go to get out past the event horizon. Each path just leads you right back to the center of the black hole. As you get closer and closer to the event horizon, space-time is warped more and more. And this causes a steep gradient in the gravitational field. So what that means is basically if you were falling into a black hole feet first, your feet and legs would be pulled more than your head and neck. You would be stretched out like this astronaut here falling into a black hole. And eventually you would be torn apart by this difference in gravitational force. And this is called, and I promise I'm not joking, spaghettification. I've also seen it called the noodle effect, which honestly is just as silly. What you are eventually heading for once you cross the event horizon is something called the singularity. Now, we can't see beyond the event horizon, but general relativity predicts that at the center should be a gravitational singularity. For a simple, non-rotating black hole, this is a single point in space that has zero volume and infinite density and contains all of the mass in the black hole. Once you cross the event horizon, you have a one-way ticket to being smooshed into the singularity. Those are really the two main things that make up a black hole, but I do want to point out one more feature, and that is something called the photon sphere. So it's kind of this swirly light. So a photon sphere is made up of photons or light that is trapped in a circular orbit around a black hole. This tends to be not at the Schwarzschild radius, but a little bit further out, about 1.5 times the Schwarzschild radius. These orbits are dynamically unstable, meaning that any perturbation, any little nudge will either send a photon away from the black hole or will push it inextricably towards it. How black holes grow is actually kind of a tricky question and can get into very finicky questions of cosmology and galaxy evolution. But to put it simply, the vast majority of black holes form by the gravitational collapse of extremely massive stars. Stars can exist because of a balance between the pressure generated by the heat they produce while they have fuel for nuclear fusion and the gravitational force that wants to bring all the mass of the star towards the middle. As long as stars have fuel to burn, it can stave off gravitational collapse. But when all that fuel is spent and the star is massive enough, there's nothing to keep the star from collapsing in on itself. So that's how astronomers think most black holes form. Once they form, they can grow their mass by accreting more matter, so gobbling up matter in space. It's a common misconception that black holes suck up matter like a vacuum, and that is not true. When you are quite close to a black hole, it can be very hard to escape, but you have to be very close. But when stars or gas or dust get close enough to a black hole, the black hole can siphon off some of that matter and add to its mass. Also, because black holes are thought to reside at the center of every large galaxy, when galaxies merge, when they collide, so do their black holes. So we can't really see black holes, right? That's kind of like one of their main things. But we've definitely had indirect observations of black holes, the first one being of black hole Cygnus X1 in the early 1970s, located in the middle of the neck of the constellation Cygnus the Swan. So right here where there's a red circle. So sometimes accretion disks will form around a black hole, and the gas closest to the black hole will orbit extremely fast and will heat up and emit strongly in X-rays. So Cygnus X1 was identified as an X-ray source in the 1970s. First, astronomers didn't know they had found a black hole. They first identified a blue supergiant star from watching and measuring the energy output of that star. They noticed that there was a compact object nearby. Analyzing the orbit of the companion star, so the orbit of that blue supergiant, led astronomers to estimate the mass of Cygnus X1 to be 21 times the mass of the Sun. From pulsations of energy from this source, astronomers determined that this object was extremely compact, about 600 kilometers across. Only one thing can be so massive and so compact, and that is a black hole. Without the companion star, honestly, who knows whether we would have found Cygnus X1. The accretion disk around the black hole, so this disk of gas and dust swirling around the black hole, was supplied by the companion star. Stars produce a stellar wind, which blows off particles into space. The companion was close enough to Cygnus X1 that the black hole could capture those particles onto an accretion disk. Matter in the inner disk heats up to millions of degrees and produces X-rays, and the energy of the infalling material is ejected even further out into space by jets. And you can see on the screen an image of Cygnus X1 in X-rays. You can see it's very bright, and at the top, an artist representation of what this system may look like. So you have this big blue companion star and the black hole kind of siphoning off this material into an accretion disk. While we still mostly identify black holes by their effect on their surroundings, we have actually come a long way in imaging a black hole. So back in April of 2019, astronomers using the Event Horizon telescope released the first image of a black hole, which is counterintuitive because I really just said that we can't see a black hole, so how can we image it? It's probably more accurate to say that astronomers image the black hole's quote-unquote shadow. And that shadow is of the black hole in the middle of a galaxy called M87, which is on this side of your screen. It is a giant elliptical galaxy in the Virgo cluster, about 53 million light years away. It also has a supermassive black hole at its center with an estimated mass of 6.5 billion times the mass of the sun and is 22 billion miles wide, which is actually only 0.004 light years. So this is how the black hole M87 compares to its host galaxy. So again, pretty massive for a single object, but actually kind of small compared to the galaxy as a whole. We know that M87 has a jet. Right here you can see the jet in blue, and this implies the existence of an accretion disk, like with Cygnus X1, and an estimated 90 Earths worth of mass passes through the event horizon every single day. The image on your screen here is the image produced by the Event Horizon Telescope team. And the dark part in the middle is what they call the black hole shadow. And it is surrounded here by this glowing photon sphere. Remember, the photon sphere appears a bit further out than the actual event horizon. So this is really the best picture we have gotten of a black hole to date, and will in the future lead to advances in understanding how black holes affect their host galaxies. The black hole inside M87 is not the only black hole to be imaged by the Event Horizon Telescope. They've also imaged the black hole at the center of our own galaxy, called Sagittarius A star. So they released this image at the top of the screen back in 2022, and estimate that our own supermassive black hole is merely 32 million miles across and only weighing in at 4 billion times the mass of the sun. Really, compared to M87, Sagittarius A star is a bit of a lightweight. But it was the subject of the 2020 Nobel Prize for Physics that went to Reinhard Genzel and Andrea Ghez for showing that Sagittarius A star was even a black hole to begin with. They showed this not with imaging the black hole, but by indirect observations. They carefully measured the orbit of stars that orbit close to the center of the Milky Way, and showed that from characteristics of the star's orbit, that there must be an extremely compact and massive object at the center, a black hole. And that's what you saw in this video. The orbits of stars indicate that something very massive, but comparatively small, is at the center. I think it's interesting to compare the black hole in M87 to Sagittarius A star. One of the reasons the image of M87 was released before Sagittarius A star was because even though Sagittarius A star is closer to home, it's in our Milky Way, the M87 black hole is so much bigger that it was actually easier to image. You can see from this comparison image, right? We have M87 star, Sagittarius A star. The shadow of M87's black hole extends much farther out than the orbit of Pluto does in our solar system, but the entirety of Sagittarius A star, the photon sphere, would fit within the orbit of Mercury. Both of these are considered to be supermassive black holes, and they are, right? They're billions of solar masses, but there is still a vast difference in size. The difference in mass between these two black holes actually does make sense and was expected. M87 is a much more massive galaxy than the Milky Way. According to our current understanding, black holes at the center of galaxies tend to grow along with their galaxies. So we expect more massive galaxies to have more massive central black holes. Black holes used to be the stuff of theoretical prediction and not necessarily thought to be real things in the universe. The last couple of topics I'd like to cover today are right now also kind of in the realm of theory, but in a different way. With black holes, we had a theory of gravity that seemed to work really well, but predicted these really weird things might happen if you get too much matter in one place, and observers went out to look for them. But with dark matter and dark energy, the last two topics I want to discuss, observers measured the universe and realized that something wasn't right and that we needed some new ideas to make the universe make sense again. So let's start with dark matter. So this chunk of the pie chart. Dark matter makes up about 25 to 27% of the universe, compared to 5% made up by ordinary luminous baryonic matter. This means really that 80% of the mass in the universe is dark matter. And this is quite honestly a bit of a problem from an observational standpoint, because dark matter is called dark because it does not interact at all with electromagnetic radiation, aka light. If it doesn't interact with light, then how can we see it? Well, like black holes, we look for ways in which it affects its surroundings, because also like black holes, we can see the effect of dark matter because it has gravity. And there are several threads of observational evidence that lend support for the existence of dark matter. The first and probably most well-known are galaxy rotation curves. So an example of a rotation curve is on the top of your screen here. It's just basically a plot of the speed of a spiral. The spiral galaxy is rotating as a function of distance from the center. So we have a rotation speed on the vertical axis, distance from the center on the horizontal. If we assume that the only mass in the galaxy is what we can see, the stars, the gas, the dust, the planets, we would expect the rotation speed to decrease as you get further out into the outskirts of a spiral galaxy. The rotation curve would kind of follow this red line, kind of slowly just go down as you get further out. So this is what Kepler's second law of orbital motion tells us, because not only is the distance getting bigger from the center, but the amount of mass that we can see gets smaller. But this is not actually what we find. Starting as early as the 1960s, some astronomers noted that the outskirts of spiral galaxies seem to be moving faster than we would expect them to. In the 1970s, Vera Rubin showed that this was definitely true. Rotation curves of spiral galaxies follow something more like this green line in the plot on your screen. We say the rotation curve is flat. She measured the rotation curve of several galaxies and determined that more matter was needed to make the rotation curves she was measuring work. Similar work has been done on elliptical galaxies. For elliptical galaxies, you don't measure a rotation curve because there's no rotation. Elliptical galaxies are kind of those big, just fuzzy patches in the sky. Instead, you need to measure something called the velocity dispersion. So this is basically a measure of how varied the velocity of individual stars are in an elliptical galaxy. like how fast they're going and in what direction. By measuring the velocity dispersion, astronomers can come up with an estimate for how massive the galaxy is. And surprise, surprise, our measurements do not match our predictions. We've also seen evidence of dark matter through something called gravitational lensing. Okay, so according to general relativity, space and time are one thing called space-time, which is something that matter can distort. This space-time distortion manifests to us as gravity, but distorting space-time, or by distorting space-time, matter can alter the path of light or other matter traveling through space. As a consequence, if something as massive as a galaxy cluster, which you kind of see on your screen here, which can include thousands of galaxies, is in between us and a faraway galaxy, the massive galaxy cluster will bend and distort the light coming from the background galaxy. This is called gravitational lensing. It's most commonly used with galaxy clusters because there's just so much mass there and so much distortion, but it can also be done with a very massive lone galaxy, which you can see down here. So on the screen now are examples of galaxies lensed by a galaxy cluster and galaxy lensed by a lone foreground galaxy. In both images, the lensed galaxies are distorted, some stretched, right? So they look like streaks in the sky. This foreground galaxy, it's almost a perfect circle, right? And then there's some other lensing that's a little bit more subtle. But we can use this distorted light from the background galaxies to estimate the mass of the cluster. The more distortion, the more massive the cluster. And once again, an estimate of the masses of galaxy clusters using this method indicate that there's heaps of matter that we can't see. Galaxy clusters are actually good test beds for dark matter because there are many different ways to measure their mass. We can measure the radial velocities of the galaxies within it, which is kind of like the same method we would use to estimate the mass of an elliptical galaxy. We can also estimate the amount of mass within a cluster by measuring the amount of X-ray energy emitted from the cluster, as well as the aforementioned gravitational lensing. All of these methods agree that dark matter outweighs normal matter by about 5 to 1. There is one cluster in particular that is considered extremely good evidence for dark matter, and that is the Bullet cluster. The Bullet cluster is a recent merger of two massive galaxy clusters to make one even more massive galaxy cluster. Most of the mass in galaxy clusters is not in the galaxies themselves, but in the hot gas that surrounds and permeates the cluster. When galaxies collide, the galaxies themselves are not really bothered. It seems like this would be a really disturbing event, but galaxies are big, but space is bigger. So in the beginning stages, at least, of a merger, two groups of galaxies will just kind of go through each other without anyone really noticing. So we say that these galaxies are collisionless. But that's not true for the hot gas. The gas does interact, and when gas molecules collide, they heat up and create friction, and that causes a kind of drag. So the gas in each cluster will kind of trail behind the cluster of galaxies. Okay, so this is how the galaxies, gas, and dark matter have been distributed in this merger. So the gas, where remember most of the regular matter of clusters should be, is in this pink area. The two galaxy clusters that are colliding are circled here in yellow. The blue is where the mass is. where it's been measured via gravitational lensing. So most of the mass in this cluster should be, if there's no dark matter, with this gas and not with the galaxies themselves, right? This should affect the center of mass of the cluster, kind of the quote unquote balance point for the cluster. And for the bullet cluster, it's not where we think it should be, naively think it should be. The center of mass actually shows up where we would expect it to be if most of the matter lived with the galaxies. So the center of mass is extremely and to high precision measured to be offset from the center of mass for the regular matter. One of the properties of dark matter is that it is also collisionless. So it would have no problem keeping up with the galaxies as the cluster merged, even as the gas was kind of stripped and left behind to catch up. So this is widely considered to be some of the best evidence for dark matter to date. And it's something that alternative gravitational theories have struggled as of yet to explain. Dark matter can be a pretty frustrating topic because we have all this evidence that it's there, but so far it's been basically impossible to learn that much about it. We still don't know very basic things like, why doesn't it interact with radiation? Why is there so much of it? And like, what is it actually? We don't even know if there's a particle out there. And I can't answer these questions right now because I simply don't know. And if you think this is frustrating, then dark energy is going to be off the charts. So dark energy is thought to make up about 68%, 70% of the mass energy budget of the universe. So 68% of the universe as we know it is dark energy. We think it's the cause of the expansion of the universe and that it uniformly fills otherwise empty space. So if you can find a spot in the universe that doesn't even have a speck of dust or a molecule of gas, it's still not empty because there's dark energy there. Dark energy is thought to be a property of space itself, and this has major implications for its effect on the universe. So think about a box of gas. If we increase the size of the box, but not the amount of gas, the density of the gas will decrease, right? The amount of gas molecules doesn't change, but now they just take up a larger volume, which makes the density of the gas decrease. This is importantly not how cosmologists think dark energy works. Cosmologists think that this is like a negative pressure, this repulsion that we see does not get diluted when there's more space. So as dark energy causes the universe to expand, it's not diluting itself in the process. It's actually kind of making itself more powerful. It's such a wild thing to think, right? So why do astronomers and cosmologists think dark energy exists? And the answer comes in our measurements of supernova. So evidence that the universe is expanding, accelerating that it's expanding, came in 1998 when a team measured the distances to several type 1a supernova. So these are what astronomers call standard candles, meaning that we know the intrinsic luminosity, the intrinsic brightness of a type 1a supernova. So we can calculate how far away they are to pretty high precision. You can compare these distances to the shift in the supernova spectra and calculate how fast the supernova is moving away from us. Cosmologists at the time expected that gravity would stop the expansion of the universe. So they expected to find that the expansion of the universe would be slowing down. What this team of astronomers found, though, was that the expansion of the universe was actually speeding up. This was a very unexpected result and has been confirmed by other independent studies. There has to be additional energy to make this possible. So far, what we've come up with to explain it is what we call dark energy. But we really don't know what it is or why it is. The details of dark energy, to whatever extent it really exists, has implications for the fate of the universe, really, and we are still desperately trying to figure it out. I want to note that dark matter and dark energy don't necessarily have anything to do with each other. They're not necessarily related concepts. They are different things, and scientists are studying them in different ways. The one thing they have in common, though, is that even though they make up 95% of the universe, we know almost nothing about either of them. I really hope you've enjoyed our journey today through dark astronomy. I just remember, just because nothing seems to be there does not mean it is not interesting. I hope you can join me next month when we'll talk about Cecilia Payne and how she revolutionized our knowledge of stars. I'll see you then.